Okay, hello guys. I will be doing an AP Chemistry FRQ from the most recent AP exam 2026. I will be doing question 3 version J as a part of my AP Chemistry final. I will be doing this problem specifically because it's an acid-base FRQ, which I chose to do my final on Unit 8 acids and bases. Okay, let's begin. So for part A, I'm sorry, I've gone through this a couple times. I'm kind of rushing through it. So we see our equation, right? Our equation of the ionization of nitrous acid. We're given a Ka and we're given a temperature. So for part A, identify a conjugate acid-base pair in the equation, and then be sure to clearly label. Since we know that nitrous acid is our acid, we can write this down as our acid, and our conjugate base is going to be just that nitrous acid once the proton is donated. So it would just be without the H because that's our proton. We have a negative charge, conjugate base, which is on the other side. We see that right there. Okay. Part B, a solution of nitrous acid with an initial concentration of 0.125, 0.125 has a pH of 2.09. Calculate the value of the hydrogen ions or hydronium ions in the solution. Show the work that leads to your answer. So if we just remember that pH equals negative log of our concentration of hydrogen ions, then we can just work this out to go backwards. So then we would get our answer by doing 10 to the negative pH, which would be 10 to the negative 2.09. Put this into the calculator, and we get 8.1 times 10 to the negative third. So that is our answer for the first part of part B. Second part of part B, calculate the nitrous concentration of nitrous acid at equilibrium. Show the work that leads to your answer. Okay, so since we're given an initial concentration and we know that we're going to calculate concentration at equilibrium, we're going to use an ICE table, which is initial, change, and equilibrium. And then we write our dissociation equation above here. Okay, so we know that we have an initial concentration of 0.125. And we start with none of this, 0, 0, because they're products. And so if we look at the ratio, the mole ratio, we know that for this, since it's a reactant producing products, we're going to lose an X amount of this. We're going to gain an X amount of this. It's a product. We're going to gain an X amount of this too, because they're equal mole ratios. So then at equilibrium, we're going to have 0.125 minus X. And right here, we're going to have X and X. Okay, so these equilibrium concentrations are what we're going to use in our Ka expression. And since we're given our Ka, we can just work this out to find what X is. So if you remember our Ka expression, which would be products or reactants or conjugate base and hydrogen ions over acid, weak acid. Okay, so now that we have that, we can just substitute our values that we know in for it. So we are going to do 5.6 times 10 to the negative fourth equals x squared, because these are both unknown right now, x squared, and just x times x equals x squared. And then on the bottom we have 0.125 minus x. But remember, our 5% exception rule is that if our Ka is very low, which is lower than 1.0 times 10 to the negative third, we can get rid of that x because the change would be so little that it wouldn't make a difference. So we'd put 125. Then we would just move this onto the other side and then square it. So if we just do that, square root of 5.6 times 10 to the negative fourth, and then times 0.125, and then our square root. So from this, we would get, let's plug it into our calculator. we would get 8.3 times 10 to the negative third. Okay, so that will be our concentration of nitrous acid at equilibrium. Okay, so now for part C, in an experiment, the solution of 0.125 molar nitrous acid is heated to 333 Kelvin. The new equilibrium concentrations are determined. So we have our new concentrations. So calculate the Ka. So this is easy. We would just plug these in, right? We already know the equation. So we would just plug in 0.0109 squared, since both things on top are the same concentrations. They're going to times each other, over 0.114. We plug this into the calculator. 0.0109 squared over 0.114 gives us 1.04 times 10 to the negative third. All right, so now we're going to need this to do part 2 of part C. So it says, is a reaction represented by equation 1 endothermic or exothermic? Justify your answer by comparing Ka values at the two different temperatures. Okay, so we know this is our Ka value at 333 Kelvin. And we know our given Ka value at 298 Kelvin is 5.6 times 10 to the negative fourth at 298 Kelvin. So if you look at these, we can see that this one is bigger than this one, right? And this is after we added heat. So if we were to think about heat as a product or a reactant, which one would make the equation shift towards the product side? Because remember that our K value is products over reactants. If we have a greater Ka value, we would need greater products. It works just like a fraction. So since we have more products in the one with increased temperature, what would make the equation shift to the product side if our heat was a product or a reactant? If we think back to Le Chatelier principle, we know that heat will be a reactant, since adding heat on the left side of the equation would cause an excess of reactants, but would cause a shift to the right side, creating more products and therefore giving us a greater Ka value. So, and finally, since heat is a reactant, that means this reaction absorbs heat, therefore it is endothermic. Let's move on. Part D. In a second experiment, a student is given a bottle containing nitrous acid with an unknown molarity. To determine the concentration of the nitrous acid in the bottle, the student titrates 34 milliliters of the nitrous acid with 0.16 milliliters of sodium hydroxide at 298 Kelvin, which reacts according to equation number 2. Equation 2. Okay, so part D. Use figure 1 to identify the pH at equivalence point. So we know that the equivalence point is going to be the middle, the exact middle between the two inflection points, or the little, these things. So if we look closely to the middle, we see that this is really where it starts to get linear for both. So we go 1, 2, 1, 2. Okay, so we're in between here. What's right in the middle? It'll be pH. We can estimate to be about 8.5. Okay, so now using that figure, calculate the molarity of nitrous acid in the bottle. So let's think back to what we're given. We're given that the volume of HNO2 is 35 milliliters. And we're also given that the base that we're titrating with has a molarity of 0.16. So if we know that it has a 0.16 molarity, and we just need to get the volume of the base that we used from the graph. So if we look, where's our equivalence point? We remember it was right here. We go down to the x-axis. We use 50 milliliters of the base. So if we think back to our molarity equation, moles over liters, we would just plug that in. 0.16 over the 50 milliliters that we used, but converted to liters is 0.05 over moles. We would bring this over to this side, and then we will multiply, which would give us 0.008 moles. Okay, so now we remember that moles of base at equivalence point, moles of base is equal to moles of acid. So now that we have the moles of base, we know that this is how many moles there are in our acid. So then, since we also know the concentration or the volume, we plug these in to find out the molarity. So 35 into liters gives us a molarity of about 0.0229. We'll say 9. Okay, so that's part E. Fix my. This looks weird. Okay. Draw an X on figure 1 to represent a point where the titration where concentration of nitrous acid is greater than its conjugate base. So if we do a little rough sketch of the titration curve, we know that this is our equivalence point. We know that this is our midpoint, if we remember. This is our midpoint. Our midpoint is where our acid is the same as our conjugate base. So if we're looking to where in the titration we have more acid than base, we would look before this line because more of the acid is unreacted with the base that we're adding, which creates more conjugate base, right? So right here, we would have more acid than base because it's a lower pH, more of it's unreacted. And then over here, we would have more conjugate base than acid since more sodium hydroxide is added and more acid is reacted with to create its conjugate base. Okay, so that was part F. We would just draw an X anywhere before the midpoint. Okay, part G. Equilibrium constants are shown in the table for the acid ionization reaction represented by equation 1 and equation 2, right? So we'll calculate the K2 for equation 2. So this is a combination of both equations that we're given the Ka and the Kw for this. This is familiar, we already know this, but we have to make a sort of combination that would equal this equation. So if we look closely, HNO2, NO2, okay, this stays the same, so we can tell that this stays the same. NO2 minus plus H3O plus. And then the other one, it looks like it flips since there's a water on this side and since there's a hydroxide on this side. So we'll try that out. We're going to flip it. H3O plus OH. And then 2 waters. So right here, we'll just cancel out, see if we end up with the right equation. Cancel out H3O and then cancel out water. And this is what we're left with. And that looks like our equation. That is our equation that we're finding for. So since we did nothing to the first equation, our Ka stays the same, 5.6 times 10 to the negative fourth. But since we flipped our other equation, we're going to have to take the inverse of our Kw, which would be, we'll just be multiplying this times the inverse, which is just 1 over what was given. Now if we do this, 5.6 times 10 to the negative fourth times 1 over 1.0 times 10 to the negative 14th. Yeah, 14th. Negative 14th. Which would give us 5.6 times 10 to the 10th. Okay, so that is our K2 value. Okay, and then finally, part H. Wait, let me delete this. What is that? Okay, part H. We'll just ignore it. Looks pretty bad. Okay. The student decides to repeat the experiment, this time using an indicator, and has access to indicators in table 2. The student conducts a second titration by adding 2 drops of methyl orange to 35 milliliters of nitrous acid and titrating the solution with 0.16 molarity sodium hydroxide until color change from red to yellow occurs. Okay, so we're doing the titration that we saw in the earlier part, but this student used methyl orange, and they're asking us to agree with him or disagree. So if we look at the table, methyl orange has a pH range of 3.1 to 4.4. And if we look back to our graph, we know that our equivalence point happens at a pH of about 8.5, if we remember. So 8.5 does not fit into this range, meaning our color change will happen before our equivalence point is reached, giving us inaccurate results. So this is not the right indicator. This is not the one we would want to use. On the other hand, thymol blue has a pH range of 8.0 to 9.6. Our equivalence point fits in here, which means our color change will happen around the time that our equivalence point will happen, which will be effective as an indicator. Therefore, we would disagree with the student, and we would say that thymol blue is a better indicator for this titration. And that is the last question. Thank you, and I hope you enjoyed.